In this video, I'm going to go over RC circuits. RC circuits are circuits that involve both a resistor, hence the R, and a capacitor, hence the C. Before we go there, let's look at a simple C circuit, namely this one here. It just has a capacitor that's hooked up via a wire to itself on the other side. What's going to happen? Well, if you imagine this capacitor is charged, right, positive one side, negative on the other, well, those negative charges, they don't like each other. They try to get away from each other as much as they can. So do the positive ones, but of course they can't really move very much because they're heavy protons. Those electrons, they're just going to leave the plate, go through the wire, which is super easy because we imagine the wire to be ideal, go on the other side, and pretty much immediately from, you can imagine there's a switch here or something that we close. The moment the switch is closed, this capacitor is going to be discharged. Everything is neutral. Everything is just sitting there. Everything is boring. Right? Within a fraction of a second, you're going to be in a situation. It just looks like this. No more charge. Realistically, it actually doesn't happen immediately. It actually takes a tiny fraction of a second. And when we study chapter 27 and talk about more realistic models for wires, we can actually calculate how long it takes for this sort of capacitor in this kind of setup to discharge. But it's boring, right? Because nothing happens. Just immediately it's discharged. That's the end of it. Well, let's make it a bit more interesting by putting the R into our circuit. So this is our RC circuit down here. Let me just change my setup a bit. There we go. Right. So this is my RC circuit. Now at this point, we first want to remember a little bit about capacitors. Right? Capacitors, they hold a charge. If they hold a charge, then there's a certain potential across them. So if I had a voltmeter, they hook up those two ends of my voltmeter V, and I get a delta V. Let's put it like this, right? That I measure from one side to the other. That delta V relates to the charge via the capacitance. Namely, capacitance was defined as charge held per potential difference. So that means it's going to be the charge Q divided by C, the capacitance. So this is let's just label it. The charge on the capacitor. But that, of course, I mean how much positive charge is on the positive side, how much negative charge is on the negative side. And C is the capacitance, and hopefully remember that the capacitance just depends on the geometry, essentially, of your capacitor. How big are the plates? How close are they together? If it's a parallel plate capacitor, if it's some other setup, well, it depends on the size of your spheres, radii of your cylinders, or however you're planning to build your capacitor. But it doesn't depend on the properties of, say, the charge that's right now on there, right? It's just kind of the physical setup. What does it look like? It'll determine the capacitance. And apparently I have a hard time actually spelling that word to the end. Right? So that is our setup. It was because C was defined as Q over delta V, charge held per potential difference across it. Now, we imagine we start off with this capacitor fully charged up. How might you get it there? Well, there's no battery in this circuit. It's something to be aware of, right? In all the other circuits so far we had batteries. But to charge it up, you might want to sort of hook it up somehow differently in the first place to charge it up. Not going to worry about it right now, though in a bit we're going to look at a similar example where we put a battery into the circuit and it allows us to actually charge up the capacitor. Okay. So if there is a potential difference across this capacitor, then, well, there must be the same potential difference across the resistor because of, well, if you like, Kirchhoff's loop law, right? If you go once around a loop, then if this side here is a certain potential difference higher than this side, then this is the same potential difference higher than that side, right? So we've got the same delta V across the resistor. Notice that I'm not assuming that either the charge or the delta V, that they're constant. They're not going to be, they're going to change in time. That's something we didn't see with resistor circuits, right? With resistor circuits, there was a delta V. Because the resistor, we didn't know what it was. We worked it out maybe, but it didn't change, you know, over time. This one will change over time, right? So, but what I write down here, that's true. You know, maybe later on there's less of a potential difference and less charge. That's okay, right? So, in a way, if you like, there's an time dependence, charge and delta V and so on. And we're going to work out what that is across the resistor. So what does that imply? That implies there must be a current through the resistor. That current is going to be the potential difference divided by the resistance. It's a resistor. It obeys Ohm's law. So which way is the current up here? Well, this is the positive side, this is the negative side. So the negative charges, they want to go this way, right? They want to go around this way, clockwise. Positive charges want to go counterclockwise, because current is defined in terms of the positive charges. Even though we know that really it's negative charges that are actually moving, the current is going this way. Going this way and then come back and go into here. Really, it's the negative charges in here that go the other way, but negative charge going this way is the same as positive charge going this way. Okay, so now the current through the resistor, right, means how much charge per second, right? That's what current means. The charge flowing per second. Well, where does the charge come from? There's no charge elevator that lifts up charges. It's coming, of course, from the capacitor, right? There are excess charges here, and they're going to go around to the resistor and then enter the other side. Of course, by doing that, they're going to gradually decrease the amount of charge that's sitting on the resistor. Let's figure out how those are related. So current is charge per second, right? Now, because if this is a 1 amp, right, the current is 1 amp, then it means 1 coulomb per second. So the charge here is decreasing by 1 coulomb per second. So we get I is minus the rate of change of charge. And at this point we have to use calculus, right, because it's a rate of change. Current, in this case, is minus the rate of change of charge. The minus sign is because it's going out of this resistor, out of the, capacitor here, right? So don't look at this equation, write it down on your equation sheet and never think about it again. No, right? The minus sign is here because of the particular setup. I see, okay, the current goes this way, the capacitor is discharging. Let me make a note of this. The minus sign is there because the capacitor is discharging. It's losing its charge. Right? So the current to the resistor is, if it's positive current, it's going to lead to a negative rate of change of charge. It's losing it. That's why there we have a minus sign there. Okay. So let's put the pieces together. We have that the charge on the capacitor is equal to the potential difference, but we also have that the potential difference is equal to I times R. Let's write this down. we have delta V is equal to I times R for the resistor. The delta V across the capacitor is the same delta V. Must be, we had it up here, charge over C, Q over the capacitance. But we also had that I itself is minus the rate of change of charge with time. And I can't write, say, delta Q over delta T because over, say, a finite time interval, because the current might be changing constantly. In fact, it will be doing that, as we'll see. Right? So I imagine it's just, if I take a tiny time interval dt, imagine it's infinitesimally small. Well, what's the infinitesimal amount charge lost? That ratio, that is my current. Let's put the pieces together. Those two are equal, so I can set this equal to this and plug the I goes into here. So I'm going to get that minus dq dt. Now I could write times R is Q over C, but I'm going to take the R to the other side, is Q over RC. So multiply the resistance by the capacitance. You can think about the units of this. It is the resistance times capacitance. Ohms times farad gives you seconds. Try to figure that one out. So, but this is the equation I'm going to get. Right? So just by combining this and this. So what is this equation telling me? It's saying that the rate of change of charge with time, up to minus sign, is equal to the charge that's still on there, divided by R and C. Right? So minus, and write out in words to make sense of it, minus the rate of change of charge with respect to time is equal to charge still left divided by, well, R times C. We know what those are. Those are just constant that depend on the resistor and the capacitor. So how do we deal with this? This is what we call a differential equation. And I strongly suspect that the majority of you have not yet taken a course on differential equations and how to solve them, how to deal with them. Sooner or later you will have to, because it's just something you'll need in physics a lot. They keep coming up. What is a differential equation? A differential equation relates a quantity to its own rate of change. Let's write this down. We have a differential equation. What is it? Writing this. It's an equation relating a quantity to its own rate of change. Could be with time, could be with something else. In this case, here it is the rate of change in time. So the question becomes, well, we can't solve this just for Q. There's no like single value of Q. We can't rearrange this in any way. But you want to figure out what function Q of T, what charge is a function of time? What's the correct mathematical expression that makes this true? We want to find the function Q of T that makes the equation true for all times, because that'll tell us what the charge is as a function of time. Right? This equation is always true. It's true now. It's true a second later. It's still true 2 seconds later. So whatever q as a function of time, charge as a function of time we come up with, it better make this always true. So that's our goal, right? It's the goal of solving the differential equation is to find a function that makes the differential equation, I'm going to abbreviate it, diff equal true. True at all times. Now that's very different from a normal, say, algebraic equation where you might try to solve, say, for the value of c in terms of x and y, or whatever the quantities are. You're trying to just get a value, maybe in a symbolic expression for it, but you're not trying to find a function in a normal algebraic equation. You're trying to find a value. In a differential equation, the solution of it is a function, or sometimes a whole list of functions, a so-called family of functions. So let's see how we find that. Now, in general, there are a large number of techniques to solve all sorts of differential equations, right? You're not expected to know these for this course, and I'm not going to test you on those. But let's just see what we can do, right? So you want to solve this one here. Let me write it down again, just so we have it at the top of the page. Our equation is minus dq dt is equal to q over rc. Okay, so what is it telling us? The time derivative of q is equal to, we write like this, q is a function of time, is equal to the function itself up to a minus sign on this side and rc on the other side. So, what function makes that true? Maybe we take a guess. How about we guess? Let's guess. Maybe we say, okay, I'm going to say it's q, the function of time is, maybe it's linear. And how about it's linear? How about we go with a times t plus b? It's our guess. Right? We don't know how to solve differential equations in general. Let's just, have a wild stab in the dark and hope for the best. So, okay, so that in the right-hand side of my equation, this part here, RHS, right-hand side, I hope you can know what I'm saying there, is going to be AT plus B. I'm just plugging in over RC. Okay, what about my left-hand side? Well, I need a time derivative. The time derivative of this is just going to be A, right? Because this is a constant. Time derivative, t just becomes nothing. So I'm going to get minus A. Okay, is the left-hand side equal to the right-hand side? No. There is a time you can find, right? You can find a single value of time where this is equal to this. But that's not what we want. We want the left-hand side to be always equal to the right-hand side, and those two are clearly not the same, right? At time equals 0, this is B over RC. This is A. No, they're not the same. I mean, you could then maybe fix A and B with a particular value, but then you put in t equals 1, and again it won't work, right? So this is not it. It was a bad guess. Okay, so let's try. Let's think about this in a little bit more detail. So this didn't work out, right? So let's simplify it a little bit. Let's imagine I want a function f, use f instead of q, and I say that df dt is equal to f. What's that? Okay, now think to your calculus course. What function is its own derivative? Now, again, maybe you don't remember, but with a bit of thought, go through your old notes, you say, f is e to the t. Because remember, e to the t differentiates to itself. Actually, there could be some kind of constant in front. Let's say let's call it something like f naught, right? So this is some constant, arbitrary constant. Arbitrary constant. So it's usually, not usually, but often we call it kind of the function name, and then with the subscript 0. Not necessarily, but you see that a lot. It's some arbitrary constant, right? Because if you multiply this by a constant, 5, and multiply this by 5, the equation is still true. E to the t differentiates to itself. You can check, yes, this is going to work out for all times. But that's not our equation. If we had, and I'm just going to add this here, if we had a minus here, how would we change that? Well, to get a minus sign when we take the derivative, how about we just put the minus sign up here? Again, you can check that's going to work out. So we're using our intuition here, our experience with functions. So you can sort of play around with it. Right? So you play around with it some more, and what we find is the function that makes this one true. It's going to be an exponential, e to the t, but we want to get a minus in this RC factor when we take the derivative. You can check that the following works out. We're going to take an q to be e to the minus t divided by RC. You take this, and at this point you pause the video, you take this function, you differentiate it, and you check that if you plug the derivative in here and the function itself in here, left hand side equals the minus side for all times. Right? The time dependence cancels out. Check it. Right? If you check it, like, you want to understand what these differential equations are, even if you don't yet have the tools to solve them systematically. Now actually, because there's q here, dq dt here, if we multiply the q by a constant, the constant is also here, so it's kind of arbitrary. Let's call this q naught. It's going to be our solution. This could be 5, 10, 100, 0.02, who knows? This will be a solution for any value. This solves the differential equation. And really you want to check this. Right? Even if you can't solve them yet, you can't look at an equation and be like, what's the answer? You don't know the techniques yet unless you've taken a differential equations class before. What you can do is you can check that the thing I claim is a solution is actually a solution. Okay. So we figure this out. What is it telling us? It's telling us that, well, the laws of nature, and if you like, which led to this equation here, allow for the charge on the capacitor to look like this. So let me write this down again. I'm just going to copy this out. We have that qt is some initial charge. Oh, I said initial charge. This is constant for now. Minus t over rc. Okay. What is the meaning of q naught? Well, let's figure it out. Again, we're just going to like inspect this, and I'm going to claim at t equals 0, right? Q of, I guess, 0. Q at the charge at time 0 is q naught. Because e to the minus 0 over rc, that's e to the 0, that's just 1. Right? So at t equals 0, this whole thing here is 1, you're just left with q naught. So q naught is our initial charge. So if we know that we start with a certain amount of charge in the capacitor, that is the amount of, say, 3 coulombs. We're going to plug 3 coulombs in as the constant here. And then if we come in a second later, well, the charge that's left is going to be given by the charge we started with times e to the minus 1 second over rc. Let's plot a function of this. Then we're going to put the charge. Here I'm going to put time. So at time equals 0, the charge is Q naught, some finite value, 3 coulombs, 5 coulombs, whatever you have in your capacitor. We'll put it here. Now, if you plot this function, e to the minus t over rc, it's going to have this kind of shape. It's called a decaying exponential. Those are hugely important in physics more broadly. For example, if you study radioactive processes and you ask yourself, how much plutonium do I have left if I come back after an hour of plutonium decaying, this kind of function is gonna come up. Or if you you let an object you let an object fall, and it's gonna hit some kind of, it's gonna reach a certain speed, and then say a skydiver, and the skydiver opens their parachute, they're going to slow down, their speed is going to, again, have a similar shape to this. Not exactly the same, but very similar. So just mathematically, those types of functions, they come up a lot, namely every time, right? Just mathematically, every time you have a differential equation that looks like this, where the rate of change of something, the minus sign, is proportional to the thing itself. In this case, charge. With air resistance, the rate of change of speed due to air drag is proportional to the speed itself. You get a similar relationship. So they come up again and again. We're studying them in the context of RC circuits. To figure out, say, what's the, how long does it take for it to be like discharged to half the original charge? Well, you can think about how to do that. In the homework preview for chapter 28, I go through an example where I work that out explicitly. Okay, so this is a time-dependent system, right? If I come back after 1 second, there'll be this amount of charge left on it. If I come back after 2 seconds, there'll be this amount of charge left on it. It depends on the resistance and the capacitance. And just from your understanding of exponentials, or just play around with the numbers, plug in some numbers, get a graphing calculator, graphing website or app, plug in some numbers, and see how the decaying exponential depends on what you've on the values of R and C. And what you should find is the bigger the resistance and the bigger the capacitance, the longer it takes for the thing to discharge. And I hope that makes sense. More resistance means you're going to get less current. More capacitance means you're going to have more charge for the same potential difference, or equally a lower potential difference for the same amount of charge. By the way, as an aside, sometimes you see this written as Q naught e to the minus t over tau, Greek letter t. The t is Rc, and this is sometimes called the time constant. This is a more general term that's used in exponentials to figure out, to determine the rate of decay of such an exponential. Okay. Let me now quickly come to a different type of RC circuit. Actually, let me not. I'm going to stop this video here. I'm going to put the second example of an RC circuit into a separate video. I realize this is already 29 minutes long, so you're probably tired. Go take a break, get a cup of coffee, get a piece of cake, whatever it is that you like, and then come back for a second video in which I'm going to go over an RC circuit that also involves a battery.